Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to solve some numerical problems on ASK, FSK and PSK. So already we know that what is ASK, PSK and FSK. So these are the digital modulation techniques. So in theory, we know that how to generate and detect these digital modulation techniques. Already we know that what are the classifications in digital modulation techniques like binary, IARE techniques. So these three come under binary digital modulation techniques. Okay. Now coming to the course outcome. Actually, this digital modulation techniques come under module 4, which is covered by 4th course outcome. Okay. So what the 4th course outcome states: analyze digital passband communication schemes using modulation and demodulation process. Okay. So now we are going to solve some numerical problems on these 3 modulation techniques. Okay. Yeah. The first one. A binary ASK system for equally probable messages uses 100 microsecond waits and channel has A0. A0 means noise spectral bandwidth is 1.338 in 10 power minus 5 watts per hertz. Determine the peak transmitted pulse amplitude to maintain P means probability of error less than or equal to 2.055 into 10 power minus 5. Okay. So all the problems regarding on the probability of error and noise spectral density, okay, and their bandwidths. Okay. So now we are going to solve this problem. So first we are going to write what is the probability of error of ASK. Okay. So here you are going to mention the probability of error as PE, that is equal to 1 by 2 ERFC, error complementary function, of EB by 2 N0. So this is the actual probability of error of ASK. So what is value given? 2.055 into 10 power minus 5. This is the given. So here we are going to find this EB. EB means energy per bit. Okay. So ERFC of square root of EB by 2 N0 less than or equal to 2 into 2.055 into 10 power minus 5. Here in the left hand side we are having 1 by 2. So I am sending this 1 by 2 to the right hand side. So it is as 2 into the 2.005 10 power minus 5. Okay. And again we are sending this ERFC to the other side also. So finally the square root of EB by 2 N0 is equal to greater than equal to 2.9. 2.9. And again we are sending this square root other side, squaring on both sides. You are getting the value EB by 2 N0, which is greater than equal to 8.46. 8.46. And finally my EB, energy per bit, which is greater than equal to 8.46 into 2 N0. So what the N0 value is given? Initially it is given as 1.338 into 10 power minus 5. So this is my energy per bit. But we know that EB is equal to A square T by 2. A square T by 2. So A square T by 2, you go to substitute in the place of EB, then 8.46 into 2 into 1.338 into 10 power minus 5. Okay, so here I'm going to substitute the value of EB in terms of A square T by 2. So now we know that T equal to 1 by RB. That is called as a data rate. So its value is given 1000 microsecond. So finally, A square. Here I'm going to find the amplitude. Okay, I'm going to find the amplitude. A square greater than equal to 2 into 8.46 into 2 into 1.338 into 10 power minus 5 whole divided by 100 into 10 power minus 6. So by using calci, we go to solve all this value. Then finally my A amplitude is 4.53 volts. Okay, so this is the solution for the given problem. Now coming to the second one. A bandpass data transmission scheme uses a PSK signaling scheme with x2 of t is equal to a cos 2 pi fct and x1 of t is equal to minus a cos 2 pi fct, and the bit duration is 0 to tb, and tb is equal to 0.2 millisecond and fc equal to 5 fb. The carrier amplitude and the receiver input is 1 millivolt, and power spectral density of the additive white Gaussian noise at the input is 10 power minus 11 watts per hertz. Assume that an ideal correlation receiver is used. Calculate the probability of error of the receiver. So the second problem, which is related to the PSK, here they go to find the probability error of PSK system. Okay, so the given noise spectral density N0 by 2, and the given two signals x1 of t and x2 of t. Why? Because before going to solve this problem, we must know how the PSK is represented. In PSK, we know that symbol 1 and symbol 0 is represented with the different phases. That means different means 180 degrees phase shift. So there is a PSK. So that's why they given x1 of t and x2 of t. And they given the duration as 0.2 millisecond. And amplitude, the carrier amplitude also given as 1 millivolt. Okay. So first here we're going to write A is the carrier amplitude is 1 millivolt. That is 1 into 10 power minus 3 volt. And what are the other data? N0 by 2 is equal to 10 power minus 11 watts per hertz they given. And another data they given, bit duration is nothing but 0.2 millisecond. That is 10 power minus 3 second. So these are the given data for that problem. So here you go to find the probability of error, PE. So the normalized power. So the given amplitude, you go to find the normalized power of the carrier in 1 ohm load. Here then they are not mentioned the resistor value. So we are taken as a 1 ohm load. Then P is equal to 1 by 2 A square. 1 by 2 A square. And bit energy. Why? Because here is sending in the form of bits. So the bit energy represented as EB, that is equal to PS TV. So here this is PS. So signal power, okay, PS into TB. So EB is equal to A square TB by 2. So this is my energy per bit. So 1 by 2 into what is A value? The amplitude is given as 1 millivolt. So 1 into 10 power minus 3 whole square into what is the bit duration? 0.2 milli. So it is 10 power minus 3. Okay. So after solving this one, you are getting 1 into 10 power minus 10. 1 into 10 power minus 10. So this is my energy per bit. So now what they ask, probability of error. So you must know what is the formula for probability of error of PSK. So it is nothing but 1 by 2 ERFC, error complementary function of E by N naught or EB by N naught. EB by N naught. So 1 by 2 ERFC of square root of what is my energy? 1 into 10 power minus 10 divided by my N naught, 2 into 10 power minus 11. So here I go to substitute the values, energy per bit and this noise. So finally this is equal to 1 by 2 ERFC of square root of 5. So you could find this ERFC square root of F or simply left. Third one, determine the bit error probability for BPSK system having a bitrate of 1 Mbps. The receiver receives the waveforms x1 of t is equal to a cos 2 pi fct and x2 of t minus a cos 2 pi fct. The received signals are coherently detected using a matched filter if A is equal to 10 millivolts and single-sided noise power spectral density is 10 to the power of minus 11 watts per hertz. Assume that the signal power and energy per bit are normalized. Okay. So here also they ask the probability of error of BPSK, binary phase shift key, or simply PSK. Okay, they given the bitrate or. Okay. So coming to the problem. A is equal to, what is A? Amplitude. That is equal to square root of 2 EB by T. So already we know that EB is equal to A square T by 2. Okay. So the reverse we go to apply for A. It is equal to 10 into 10 power minus 3 volts. The given amplitude as 10 millivolts. And T is equal to 1 by 10 power 6. That is T equal to 1 by RB. So they given the bitrate also. So from the bitrate you go to find the bit duration. So 1 microsecond. So EB is equal to A square T by 2. That is equal to 10 into 10 power minus 3 whole square into T, 1 micro, 10 power minus 6 divided by 2. Just I'm going to substitute A value and T value. Then what you got? 5 into 10 power minus 11 joules. So, my dear students, machine should have a calci to solve these problems. Okay. So we have square root of EB by N naught is equal to square root of 5 into 10 power minus 11 divided by N naught. What by N naught? 1 into 10 power minus 11. Then you got 2.24. 2.24. So the bit error probability will be So PE is equal to 1 by 2 ERFC of square root of EB by N naught. So this is the formula for probability of error of PSK. So we know that the value of square root of EB by N naught, we go to substitute. Okay. So 1 by 2 ERFC of 2.24. 2.24. Then its value is equal to, so here you are having tables, error complementary function tables. So by using the table, you go to find ARFC of 2.24 as a 0.0041. Okay. So here I am going to substitute this value. So probability of error is equal to 1 by 2 into, so here you go to substitute error complementary function of 2.24 as 0.0041. Okay. So finally, the probability of error is equal to 2.05 into 10 power minus 4. Okay. This is the answer for the third one. Now the fourth one. Binary data is transmitted at a rate of 10 to the power of 6 bits per second over a channel having a bandwidth of 3 MHz. Assume that the noise power spectral density at the receiver is N0 by 2 is equal to 10 to the power of minus 10 watts per hertz. Determine the average carrier amplitude required at the receiver input for coherent PSK and DPSK signal schemes to maintain the probability error as 10 to the power of minus 4. Okay. So this problem also similar to the previous one, but a little of changes they given the bandwidth. Okay. And remaining all the same, they given the bit rate. The data rate is 10.6 bits per second. From that, we go to find the time. Okay. Bit duration. And they given the noise spectral density, N0 by 2 is equal to 10 to the power of minus 10. And they maintain the probability of error as 10 to the power of minus 4. Okay. So the probability of error is given as 1 by 2 ERFC of square root of EB by N0 less than equal to 10 power minus 4. Why? In the problem they given, you should maintain the probability of error as 10 power of minus 4 less than 10 to the power of minus 4. The probability of error must be in this limit. So ERFC of square root of EB by N0 less than equal to, so you can send this left hand side 1 by 2 to the other side, or right hand side is equal to 2 into 10 power of minus 4. Okay. So square root of EB by N0 greater than equal to 2.6. And again you can remove this square root also. Then EB by N0 is equal to 6.9 or greater than equal to 6.9. And EB is equal to greater than equal to 6.9 into N0. So what is N0? Noise spectral density. Okay. So you can substitute EB greater than equal to 6.9 into 2 into 10 to the power of minus 10. So this is my energy per bit. But what they ask? They go to find the amplitude. Okay. So EB energy per bit is equal to A square T by 2, that is greater than equal to 13.8 into 10 power minus 10. So previously we know that we got 6.9 into 2 into 10 power of minus 10, you go to multiply, that is equal to 13.8 into 10 power of minus 10. Okay. So this is my energy per bit. So here you must know the time. So how to find the time? It is equal to 1 by RB, that is equal to 1 by 10 power minus 6. So A square is greater than equal to 2 into 13.8 into 10 power minus 10 divided by 1 divided by 10 power minus 6. So A greater than equal to 5.26 into 10 power minus 2. You can write this one as 52.6 millivolt. So this is my amplitude of the carrier. Okay. So this is the solution for the fourth one. Now fifth one. So the fifth one, the binary data is transmitted over a microwave link at the rate of 1 Mbps and PSD at the input of the receiver is 10 power minus 7 watts per hertz. Determine the average carrier power required to maintain an average probability of bit error 10 to the power of minus 4. So the probability of error must the limit less than the 10 to the power of minus 4 for coherent FSK. So what will be the channel bandwidth? So in this problem, which belongs to the FSK, previously we solved the PSK, but now this problem is regarding to the FSK, frequency shift keying. Okay, so we know that EB is equal to A square T by 2. We know that energy per bit is equal to A square T by 2. And here you go to know the probability of error PE for the FSK. Okay, that is Q of root EB by eta. So Q of EB, what is EB value? A square T divided by 2 eta, which is must be less than 10 to the power of 4, 10 to the power of minus 4. That means the probability of error must be in the limit of 10 to the power of minus 4. So from the Q table, or you can call as error complementary function, what it may be. So in some textbooks they can use it as a error complementary function. Okay, so no problem. So from the Q table, so Q of 3.71, you substitute all the values. That is value is 3.71, and this is equal to 10 to the power of minus 4. Okay, so A square T by 2 eta greater than equal to 3.71. 3.71. So equating this square root of A square T by 2 eta to equal to 3.71. Okay. So therefore, my AC or amplitude, what it may be, carrier amplitude or simply amplitude, no problem. Square root of 3.71 whole square into 2 eta divided by capital T. So here we must know the T. So what the given T for finding the T, the RB. So bit rate is 10 power minus 6. So here you go to 10 power 6 as for time it is 10 power minus 6. So 3.71 whole square into 2 into what is eta noise frequency as 10 power minus 7 divided by 10 power minus 6. So finally A or AC is equal to 2.35 millivolts. 2.35 millivolts. So the minimum average carrier power we can mention as 2.35 divided by root 2 for AC by root 2. So it is equal to 2.76 watts. Okay. So the channel bandwidth, another one is channel bandwidth is nothing but 1 by TB, that is equal to 1 by 10 power minus 6 and is equal to 1 megahertz. So this is my channel bandwidth. Okay. Coming to the sixth one. So binary data is transmitted over a bandpass channel at a rate of 300 BPS using non-coherent FSK signaling scheme with tone frequency 1070 and 1270 Hz. Calculate the probability of error P assuming A square by N naught is equal to 8000. Okay. So this is also recording FSK, but it is a non-coherent version and some given data also changed. Okay. So here we go to find finally the probability of error. That is, we go to find a P, probability of error for non-coherent FSK. Okay. So first you go to write the required formula and the given data. Then you are going to solve. So that is equal to 1 by 2 exponential of minus EB by 2 N naught. So this is my probability of error. But we know that EB is equal to A square T by 2. So we go to substitute. Probability of error is equal to 1 by 2 exponential of minus A square T by 4 N naught. So this is the modified probability of error of FSK. And what is the data given? They given the rate, data rate as 300 BPS. So from this we go to find the duration, bit duration, that is equal to T equal to 1 by RB, then it is equal to 1 by 300. Okay. So first you go to write the required formulas and the given data, then you go to solve the problem. So probability of error is equal to 1 by 2 exponential of minus 8000 into 1 divided by 4 into 300. You know that A square T by 4 N naught. Okay. So T is 1 by 300. So you go to substitute 1 by 300 here. So 1 by 2 exponential of minus 20 by 3. So we got to find this value. 1 by 2 exponential of minus 6.67. So finally the probability of error is equal to 6.34 into 10 power minus 4. Okay. So this is the answer for the sixth one. Now we go for the seventh problem. For an FSK system, the following data are observed. Transmitted binary data rate 2.5 in 10 power of 6 bits per second. Power spectral density of noise 10 to the power of minus 20 watts per hertz. Amplitude of received signal as 1 microwatt, not milli, it is 1 microvolt. Determine the average probability of symbol error assuming coherent detection. So this problem also regarding to the FSK. First one, you go to identify FSK. And here which type of detection? Coherent detection. And that given data rate as 2.5 into 10 power 6 bits per second and PSD of noise as 10 power of minus 20 watts per hertz. And given the amplitude. Okay. So first you go to write the required formula. That is equal to 1 by 2 ERFC square root of EB by 2 N naught. Okay, 2 N naught. And you know that time or bit duration is equal to 1 by RB. 1 by RB. So EB energy per bit is equal to A square T by 2. That is equal to 1 into 10 power minus 6 whole square divided by 2 into, here the numerator T also there. So it is given as 2.5 into 10 power 6. That is my bit rate. Okay. So by solving all this, you will get 1 by 5 into 10 power minus 18. So this is my energy per bit. Okay. And what they given PSD, power spectral density of noise, is nothing but N0 by 2. That is equal to 10 power minus 20 watts per hertz. Okay. So EB by 2 N0 is equal to 1 by 5 into 10 power minus 18 divided by 4 into 10 power minus 20. Okay, we go to substituting the energy per bit and PSD, noise spectral density. So finally, this value is equal to 5. Okay, 5. So now we go to substitute this EB by 2N0 value in the probability of error. So what is the probability of error? This one. That is 1 by 2 ERFC of square root 5. Okay. So again 1 by 2 ERFC of 2.23. So here we use the error complementary function tables. Okay. So by using error complementary function tables, we are get the value as 1.84 into 10 power minus 3. So again you go to multiply 0.92 into 10 power minus 3. So this is my probability of error of FSK for coherent detection. Okay. So 8th one, binary data are transmitted at a rate of 10 to the power of 6 bit per second over a microwave link, assuming channel noise AWGN. AWG means additive white Gaussian noise with zero mean and power spectral density at the receiver input is 10 power minus 1 per hertz. Find the average carrier power required to maintain an average probability of error PE less than equal to 10 to the power of minus 4 for coherent binary FSK. Determine the minimum channel bandwidth required. Okay. So this problem also regarding to the FSK. Okay. So here also some data is given. By using the data and the required formula probability of error for FSK, then you go to solve. Okay. So first the probability of error of FSK. So probability of error is equal to 1 by 2 ERFC of square root of EB by 2 N naught. EB by 2 N naught. Probability of error is equal to 10 power minus 4. So ERFC of square root of EB by 2 N naught is equal to 2 into 10 power minus 4. Why they given the limitation? Probability of error must be less than 10 to the power of minus 4. Okay. So ERFC of U is equal to 1 minus ERF of U. So this is a error complementary function. So ERFC means error complementary function of U is equal to 1 minus error function of U. Okay. So square root of EB by 2N0 is equal to 2.7. So EB by 2N0 is equal to 7.29. So N0 by 2 is given as 10 to the power of minus 10 watts per hertz. So energy per bit is equal to 7.29 into 2 into 2 to the power of 10 power of minus 10. So approximately is equal to 29.2 10 to the power of minus 10 joules. So this is energy per bit. So they given the data rate as 10 power 6. So the bit duration is equal to 10 to the power of minus 6 seconds. Okay. So now the average transmitted power is EB by TB, that is equal to 29.2 into 10 power of minus 10 divided by 10 to the power of minus 6. So what you got? 29.2 into 10 power minus 4 watts. Minus 4 watts. So here you go to maintain the probability of error must be 10 to the power of minus 4 only. Okay. So the minimum channel bandwidth required is approximately nothing but 1 by TB, that is equal to 10 power 6. So that is 1 megahertz. So this is my channel bandwidth. Okay. So that is 1 megahertz. Now coming to the another problem. A binary FSK system transmits data at a rate of 2 Mbps over an AWGN channel. The noise is 0 mean with power spectral density N0 by 2 is equal to 10 to the power of minus 20 watts per hertz. The amplitude of received signal in the absence of noise is 1 microvolt. Determine the average probability of error for coherent detection of FSK. Okay. So here also FSK problem similarly. So we know that the formula error complementary function by using probability of error is equal to 1 by 2 of ERFC of square root of EB by 2 N0. This is the required formula for FSK. Okay. So here you go to find the energy per bit. Okay. So we know that EB is equal to A square T by 2. So A square as 10 power minus 6 to the power of 2 by 2 into 1 divided by 2 into 10 power 6. This one. That is equal to 0.25 into 10 to the power of minus 8 joules. So there is EB, energy of bit. That is equal to 0.25 into 10 to the power of minus 8 joules. Where N0 by 2 is equal to 10 to the power of minus 20. 10 to the power of minus 20. N0 is equal to 2 into 10 power minus 20. So this is my N0, noise spectral density. So here we are going to substitute EB value and N0 value in the probability of error. Okay. So we know that the probability of error is equal to 1 by 2 ERFC of square root of EB by 2 N0. So what is EB value? 0.25 into 10 power minus 8 divided by 2 N0. So already 2 is there. So 2 into 2 you can write as directly 4. So 4 into 10 power minus 20. So this is my probability of error after substituting the value of EB and N0 value. Okay. So probability of error is equal to 1 by 2 ERFC of square root of 0.25 into 10 power minus 18 divided by 4 into 10 power minus 20. So 1 by 2 ERFC of square root of 6.25. Square root of 6.25. So here also you are using error complementary function tables. Okay. So here using the table of error functions. So ERFC of 10.2. So ERFC square root of 6.25 is equal to ERFC of 2.5 and is equal to 1 minus ERF of 2.5. Then it is equal to 0.0041. Okay. So now you go to substitute this ERFC, this value directly in the probability of error. So the probability of error is equal to 1 by 2 into 0.0041. You get written as 2.05 10 power of minus 4. So this is the probability of error of FSK. Okay. Now 10th one, or the last one. A binary data is transmitted using ASK over a AWGN channel at a rate 2.4 Mbps. The carrier amplitude at the receiver is 1 millivolt. Noise power spectral density naught by 2 is equal to 10 to the power of minus 15 watts per hertz. Find the average probability of error if the detection is first one is coherent, A bit is coherent and B bit is the non-coherent. Take ERFC of 5 is equal to 3 into 10 power minus 6. They given ERFC value directly. So you can substitute the ERFC error complementary function of 5 value directly in the probability of error. But you go to find the probability of error in two cases. The first case is coherent and second one is the non-coherent version. Okay. So this problem is ASK. Okay. So first you could write the given data. They given the carrier amplitude. So AC is equal to 10 power minus 3 volts. And the given RB is equal to 1 by TB. Okay. That is equal to 2.4 into 10 power 6 RB is given. From that you go to find the TB. And the given N0, noise spectral density, is 2 into 10 power minus 15. Okay. So these are the given data. So by using this given data, we are going to solve our problem with required formulas. Yeah, first bit energy, EB. Bit energy that is equal to a square t by 2. Directly you can write that is equal to a square or 10 power minus 6 divided by 2 into 2.4 into 10 power 6. So finally you are getting 10 to the power of minus 12 divided by 4.8. This is EB and this is the units are joules. So now the first bit is coherent ASK. Coherent ASK. So there is probability of error is equal to 1 by 2 RFC of 1 by 2 square root of EB by N naught. Okay, EB by N naught. So 1 by 2 RFC of 1 by 2 of square root. You could substitute the values. Energy per bit EB. So it is 10 cube divided by 9.6. Okay. Then you got probability of error is equal to 1 by 2 RFC of 5. Already given RFC of 5, we can take diagonally 3 into 10 power minus 6. So approximately 1 by 2 RFC of, here we substitute RFC value directly as 3 into 10 power minus 6. So the probability of error is equal to 1.5 into 10 power minus 6. So this is for coherent ASK. Okay. And the B bit is non-coherent ASK. Non-coherent ASK. So P is equal to 1 by 2 exponential of minus EB by 4 N naught. This is a non-coherent ASK formula. So we will substitute P 1 by 2 exponential of minus 10 to the power of minus 12 divided by 4.8 into 1 by 4 into 1 divided by 2 into 10 to the power of minus 15. So we will substitute all the values. EB value, N naught value. Okay. Then you got to 2.45 into 10 to the power of minus 12. So probability of error for non-coherent ASK is this one, 2.45 into 10 to the power of minus 12. Okay. I hope that you understand well. And the reference is taken for solving these problems mainly from Computer Systems by J.S. Chitodi and Computer Systems by Hyderabad also. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.